Hey everyone, we're going to be going over the malonic ester and acetoacetic ester synthesis. There's 4 questions on here and I already sent them out to the class, so make sure that you work on them before we start. So let's begin. Provide the products for the following reactions. So step 1, NaOET, that is our base, and our base is going to look from our most acidic proton. Our most acidic proton is going to be the one that I just drew out because it's in between two electronegative groups, and because if you turn this into its conjugate base, it's very stable. And so having a stable or weak base, because stable and weak mean the same thing, means that your conjugate acid was very strong. So we're plucking this proton off. As we have been doing for a lot of our reactions. So then the first intermediate step just looks like an enolate, and you can write the enolate out or you can leave it as a carbanion. I like to leave it as a carbanion because it lets me know what I'm attacking with, that this is my nucleophile, because sometimes I got confused with which one was my nucleophile when I wrote the resonance structure for this. So I have my nucleophile, and on step number 2, we're adding in our electrophile. So nucleophile comes in and attacks electrophile, and leaving group leaves. Make sure to count your carbons. So I'm adding a total of 1, 2, 3, 4, 5, 6 carbons. One, 2, 3, 4, 5, 6. Cool. Keep in mind that the alpha carbon was always there, so you have to draw it. It's not included in the 6 carbons that you're adding on. And then step number 3, I had them joined together, but I'll just do each reaction in case on the test they want to stop it at H3O+. Forgot to draw this out. So when they do hydronium ion, it's a hydrolysis reaction. So we're going from an ester to a carboxylic acid, and all of my esters are turning into carboxylic acids. There we go. And finally, the last step, heat, is a decarboxylation reaction. So whenever we see it, it takes off a whole carboxylic acid group, or it'll come off as a CO2 group. So you can choose either one because they're almost identical, but only one will come off. And knowing the mechanism for the decarboxylation reaction is very important. I can go through it in just a second, but this should be our product. Again, just make sure to count your carbons to make sure we got everything down. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So this should be our answer. Next, we are doing almost the same thing. So we'll do each intermediate. NOET, or sodium methoxide, is going to deprotonate the alpha carbon, the alpha hydrogen. And we're going to make our enolate. This enolate is then reacted with an alkyl halide. 1, 2, 3, 5. There we go. And so my nucleophile, the negatively charged carbon, is going to go ahead and attack my electrophile. and the leaving group will leave. So right now, after this first step, this is what we get. Count your carbons, so you added a total of 3 carbons. This is our next step. It's almost the same, and I'll show you the mechanism just so that we get more practice. But here's what happens. This is still your most acidic proton, the alpha hydrogen, or your only proton in this case. So you're going to deprotonate that one and put the electrons from that bond onto the alpha carbon. And I'm creating another nucleophile. And that's perfect because we just added a reactant that is electrophilic. Almost the same, but this time I'm adding only 2 carbons. Negative. Oh, never mind, I have more space. And so my product for that second step should be this. Perfect. Finally, my last step is to turn it into a carboxylic acid, or them into carboxylic acids with H3O+, because these combine are H3O+. And this is a hydrolysis reaction. Again, doing the same thing, esters to carboxylic acids, and everything else stays the same. And then finally, we have our heat, which heat does a decarboxylation reaction, again, only taking off one of the carboxylic acids. And let's see what we're left with. I think keeping in mind where your alpha carbon is and what is attached to your alpha carbon will really help. So I know that I added 2 carbons to my alpha carbon in one of the steps, as well as a little propyl group to the alpha carbon in another step. So I know that this should be good. You can always count your carbons though, just to make sure. Very quick, I don't think I mentioned it, but these two, let's call them A and let's call them B. These 2 reactions were the Malonic ester synthesis reactions. So what you need to notice is that for all the malonic ester synthesis reactions, you are using diethyl malonate as your starting material. So it's not like you're creating malonic ester, it's that you're starting with diethyl malonate. And so I can't call reactions C and D malonic ester synthesis because this is another starting material. So I forgot the name of the starting material for C and D. I believe it's ethyl acetoacetate. I need to check that, but it's a different starting material, and that's why these 2 reactions are now the acetoacetic ester synthesis. So even though they aren't going to be too far off in terms of like the reagents we use, the starting material, this right here, is different from A and B. So they're 2 different reactions, but again, the same procedures. Okay, before I go into the acetoacetic ester synthesis reactions, I kind of wanted to show a decarboxylation reaction. So I'm drawing a random one. Yeah, let's just draw this. So usually we did decarboxylation reactions when there was 2 carboxylic acids. Sorry about that. And so the reaction, I'm going to draw it in a different way so that it's easier to draw my arrows. But again, it's the same thing. You need to know the mechanism for this. It's very important because if it's definitely a question I got asked on my test for this upcoming test, and that I never really got too much practice on because I had only seen it once and I didn't think it was that important. It wasn't stressed during the lecture, but it was definitely something I saw on my test and that I had to really dig deep to get right. So starting off with the decarboxylation reaction, I grabbed onto a hydrogen from the carboxylic acid with one of my bonds for the double bond between carbon and oxygen. The electrons from this bond are put between oxygen and carbon right here, because again, we know that when we're talking about decarboxylation, we know we have to make CO2, so this bond just makes it a little bit more similar to CO2. And then finally, you can't have 6 bonds to that carbon, so you break it off and put those electrons as a double bond. And I'll show you what this looks like now. So I have CO2 gas, as well as an enol. And whenever you see an enol, you know that it can tautomerize. So I'm not done with my reaction yet because it doesn't look like what we have over here, which is a carboxylic acid, not an enol. So what I have to do is tautomerize. And then I get my carboxylic acid group. I wasn't looking at any of these examples. I was just giving you in general what it should look like. So this would be your mechanism. And the driving force for this reaction would be the increase of entropy that's created when you create carbon dioxide. So just like that other reaction with SOCl2 where we made sulfur dioxide, the driving force of the reaction was a good leaving group, the creation of a good leaving group, and the creation of increased entropy. So anytime you form gas, that's definitely a pattern that you'll see. I'll erase that. Let's see. Okay, acetoacetic ester synthesis. First step, always deprotonating your most acidic alpha carbon or hydrogen. And so you have 2 alpha hydrogens, but the one in the middle of these 2 carbonyl groups is going to be the most acidic. So I'm going to deprotonate that one. Again, it's the most acidic proton because the conjugate base is so stable or so weak. So if you have a weak base, you have a really strong acid. And then we react it with another alkyl halide. And so I have my nucleophile. My nucleophile attacks my electrophile that's electron deficient, and my leaving group will leave. So I added a total of 1 carbon to the alpha carbon. And I'll combine this last step. So we know that H3O plus, actually I'll show each one, but we know that this whole group is going to come off because the ester turns into a carboxylic acid. And we know that when we apply heat, a decarboxylation reaction that removes the carboxylic acid occurs. And so you're left off with only this. Perfect. Okay, next reaction, again, the same thing. Decarboxylation. I'm sorry, not decarboxylation. Deprotonation. So I've created a pretty great nucleophile. Nucleophile attacks electrophile and leaving group leaves, adding a total of 1 carbon to my alpha carbon. So we're done with these. And then I'm asking you to deprotonate one more time. And again, we still have that our most acidic proton is in between those 2 carbonyls. So deprotonate that one right there. Next one, another electrophile, just looks a little different. If they give you abbreviations, feel free to keep them because a lot of people always get confused with those abbreviations. So I'm going to keep my abbreviation, I'm going to attack my electrophile, and I'm going to have the leaving group leave. I don't have to draw the whole thing if I don't want to, especially if they're the ones giving me the abbreviations. Perfect. And then finally, we know that these two steps in conjunction, I guess I forgot the heat part, but these two steps in conjunction, we know that this is going to turn into a carboxylic acid, and then decarboxylation reaction occurs. So I'll just do it step by step anyways, so for more practice. Carboxylation reaction. So find your alpha carbon and then remember what you added to there. Group. And this would be my answer. Okay. So we've completed the malonic ester and acetoacetic ester synthesis. If you guys have any questions, you guys can always email me. And yeah, hope this helped.